So we have a problem of finding the minimum and maximum of the function x squared minus 4y on under a constraint. The constraint is that we have to be on the ellipse x squared plus 2y squared is equal to 8. And we're supposed to use the method of Lagrange multipliers. So let's recall how this method works. So basically, we're working on a curve in this particular situation defined by a constraint function, which, as you will see, we will need to define here. And we wish to find the critical points for the objective function f of x, y. So this is what we call the function that we wish to minimize and maximize. And it is a misconception sometimes to assume that the method of Lagrange multipliers gives us automatically a minimum or a maximum. No, it just gives us critical points, and then we have to make sure that there is a way to ascertain that a minimum or a maximum occurs at one of those points. So in any case, the bottom line is that the system of equations that we have to consider comes from the fact that the gradient of f should be a multiple of the gradient of g, and that g should be equal to 0 so as to ensure that we are within our constraints. And that's pretty much the method of Lagrange multipliers. Let's see how we apply this method to this particular problem. So we begin by defining g of xy. Just bring everything on the left-hand side. Then the ellipse x squared plus 2y squared is equal to 8 is simply the level curve of g corresponding to the value 0. Okay, so now let's apply our method of Lagrange multipliers. The system should be that the gradient of f should be lambda times the gradient of g, and g should be equal to 0. And of course, this means that the gradient of f, which is 2x comma negative 4, should be equal to lambda times the gradient of g, which is 2x comma 4y. And of course, we shouldn't forget that we have to be on the curve, so x squared plus 2y squared should be equal to 8. Let's rewrite the system as 2x is equal to 2 lambda x, and minus 4 is equal to 4 lambda y. And of course, x squared plus 2y squared is equal to 8, but we need to pursue the one equation that will give us what we want, which is the first one. Divide by 2 and bring everything to the left-hand side. We will get x minus lambda x is equal to 0, which implies that x times 1 minus lambda is equal to 0. So there are two cases from here. Either x is 0 or lambda is equal to 1. Maybe they occur both at the same time. I mean, nobody can dismiss this possibility, even though that's not so really what happens. But in any case, now equipped with these two possibilities, we follow down each one of them. So x equals 0 implies that we go to our constraint and we get 2y squared is equal to 8, which means that y squared is equal to 4, which means that y is equal to plus or minus 2, and this yields 2 points, 0, 2, 0, negative 2. If lambda is 1, then we go into the second equation that gives us minus 4 is equal to 4y, and this implies that y is equal to negative 1. Once we know that y is equal to negative 1, again, we go into our constraint function, and we get x squared plus 2 is equal to 8, which means that x squared is equal to 6, and this implies that x is equal to plus or minus square root of 6. So that gives us 2 more points, square root of 6 comma negative 1, and square root of 6, or rather negative square root of 6 comma negative 1. So we narrowed down the minima and maxima which have to exist since an ellipse is a compact set onto those 4 points. And what we do now is we simply form a table, since we know that these are guaranteed and these are the only possibilities, and we evaluate our objective function on those points. And what do we get? Well, the function was x squared minus 4y. So here we will get minus 8, and here we will get 8, and here we will get 6 plus 4, which is 10, and another 10 here. So what we get is the minimum occurs here at 0, negative 2. The maximum occurs here. The maximum occurs here. And then here's the remark that we were trying to make before. So for example, at the point 0, negative 2, we have just a critical point. It's neither a minimum nor a maximum for the specific function. I'm not saying whether it's a local minimum or local maximum on that ellipse, but certainly it's not an absolute minimum or an absolute maximum, which is what we are looking for. So in any case, this completes the solution of this problem. Thanks for watching.